Look up at the night sky, thousands of stars, each a sun like ours. Our sun, a tiny part of a giant spiral, the Milky Way galaxy. Billions of galaxies fill the universe, vast and awe-inspiring. But here's a question. What holds it all together? The stars and gas we see don't have enough gravity. They wouldn't spin in galaxies, wouldn't form clusters. Something else is out there, something we can't see, something mysterious. We call it dark matter. Dark matter is invisible to our telescopes. It doesn't emit light or energy like stars and galaxies. Yet we know it's there. Its gravity tugs on everything, shaping the universe as we know it. This invisible force is one of the biggest mysteries in science. In the 1930s, Fritz Zwicky, a Swiss astronomer, studied galaxy clusters. These are groups of hundreds or even thousands of galaxies, bound together by gravity. Zwicky measured the speed of galaxies within these clusters. He found something strange. The galaxies were moving too fast. Their speed should have flung them out into space. The cluster's visible mass didn't have enough gravity to hold them together. Zwicky concluded that there must be more mass in the cluster than we could see. He called it Dunkelmaterie, German for dark matter. Zwicky's findings were initially met with skepticism, but over the decades, more evidence emerged. Astronomers observed similar anomalies in the rotation of spiral galaxies. The stars in the outer regions were moving much faster than they should, given the visible mass of the galaxy. Zwicky's observations of galaxy clusters were groundbreaking. They challenged our understanding of gravity and the universe's composition. His work laid the foundation for decades of research into the nature of dark matter. The idea of missing mass in the universe was not entirely new. Astronomers had pondered the existence of faint stars or other objects that were difficult to detect. However, Zwicky's calculations suggested that the amount of missing mass was far greater than any known population of dim objects could account for. His findings were initially met with resistance. Some scientists questioned his methods, while others proposed alternative explanations for the observed galaxy motions. But as technology advanced and more observations were made, the evidence for dark matter continued to mount. One of the most compelling pieces of evidence for dark matter comes from the bullet cluster. This is a system of two colliding galaxy clusters, caught in the act of merging. Astronomers observed the bullet cluster using X-ray telescopes and gravitational lensing techniques. The hot gas from the two clusters collided and slowed down, creating a shock wave visible in X-rays. However, the galaxies themselves passed through each other relatively unscathed. This is where it gets interesting. Gravitational lensing showed that the majority of the mass in the bullet cluster is not concentrated in the hot gas, but rather in two separate regions that line up with the positions of the galaxies. This implies that the galaxies are embedded in halos of invisible dark matter, which interacted much less strongly during the collision. Section 5. Gravitational lensing, bending light, and finding the unseen. Gravitational lensing is a powerful tool for studying dark matter. It allows scientists to observe the otherwise invisible components of the universe. It's based on Einstein's theory of general relativity, which states that gravity can bend the path of light. This bending effect is similar to how a glass lens bends light to focus an image. Massive objects, like galaxies and clusters of galaxies, can act as gravitational lenses. These cosmic lenses magnify and distort the light from objects behind them. When light from a distant object passes by a massive foreground object, its path is bent. This bending can reveal hidden details about the universe. This can create multiple images of the background object, or distort its shape into arcs or rings. These visual effects are known as Einstein rings and arcs. By analyzing these distortions, astronomers can map the distribution of mass in the lensing object, including both visible and dark matter. This helps in understanding the structure and composition of the universe. Gravitational lensing has been used to create detailed maps of dark matter in galaxy clusters. These maps provide crucial insights into the unseen mass that makes up most of the universe. These maps show that dark matter forms a vast, filamentary network, with galaxies strung along its tendrils like pearls on a string. This cosmic web structure is fundamental to our understanding of the universe's large-scale structure. Section 6. Wimping out. The search for dark matter particles. So what is dark matter made of? We don't know for sure, but physicists have proposed several candidates. One of the leading contenders is weakly interacting massive particles, or WIMPs. WIMPs are hypothetical particles that interact very weakly with ordinary matter. They are thought to be much heavier than protons and neutrons, the particles that make up atoms. According to some theories, WIMPs were created in the early universe and have lingered in large numbers ever since. Scientists are searching for WIMPs using a variety of methods. Some experiments use large detectors buried deep underground to shield them from cosmic rays. These detectors are designed to look for the faint flashes of light or electric charge that would be produced if a WIMP collided with an atom in the detector material. Section 7. Axions. Another candidate in the dark. WIMPs aren't the only game in town. Another promising candidate for dark matter is the axion. Axions are hypothetical particles that were originally proposed to solve a problem in particle physics, but they also have properties that make them good dark matter candidates. Axions are thought to be much lighter than WIMPs, and they interact even more weakly with ordinary matter. This makes them extremely difficult to detect directly. However, scientists are developing clever experiments to search for the telltale signs of axions. One approach is to use strong magnetic fields to convert axions into photons, which can then be detected. Another approach is to look for tiny variations in the electromagnetic field that would be caused by the presence of axions. Section 8. The future of dark matter, new technologies, and deeper mysteries. The search for dark matter is one of the most exciting frontiers in modern physics and astronomy. This mysterious substance, which makes up about 27% of the universe, remains largely undetected and poorly understood. Scientists around the world are dedicating their careers to uncovering its secrets. New technologies and innovative experiments are being developed all the time, pushing the boundaries of our ability to detect and understand this elusive substance. From advanced computer simulations to cutting-edge laboratory equipment, every tool at our disposal is being utilized to its fullest potential. One promising avenue of research is the use of liquid xenon detectors. These detectors are designed to capture the faintest interactions between dark matter particles and ordinary matter. These detectors are incredibly sensitive to the faint signals that might be produced by dark matter particles. By monitoring these signals, scientists hope to gather crucial data that could lead to groundbreaking discoveries. They are also scalable, meaning that larger and more sensitive detectors can be built in the future. This scalability is essential for increasing the chances of detecting dark matter and understanding its properties. Another exciting possibility is the development of space-based dark matter detectors. These detectors could be placed in orbit around Earth, or even further out in space, providing a unique vantage point for observing dark matter. These detectors would have the advantage of being shielded from the constant bombardment of cosmic rays that plague Earth-based experiments. This shielding would allow for much clearer and more accurate data collection. They could also provide unique perspectives on the distribution and properties of dark matter throughout the universe. By studying dark matter in different environments, scientists can gain a deeper understanding of its role in the cosmos and how it influences the formation and evolution of galaxies. Section 9. Dark matter and the fate of the universe. The study of dark matter has profound implications for our understanding of the universe's past, present, and future. The amount of dark matter in the universe affects its expansion rate and its ultimate fate. If the universe contains enough dark matter, its gravity will eventually halt the expansion and cause it to collapse in on itself in a big crunch. However, if the universe doesn't contain enough dark matter, it will continue to expand forever, growing colder and darker with time. Dark matter also played a crucial role in the formation of the structures we see in the universe today. In the early universe, dark matter's gravity acted as a seed, drawing in ordinary matter and forming the first galaxies and clusters of galaxies. Section 10. The universe's unseen hand. A final thought. Dark matter remains one of the greatest mysteries in science. It is an enigma that has puzzled scientists for decades, challenging our understanding of the cosmos. It's a stark reminder of how much we still don't know about the universe we live in. Despite our advancements, the universe continues to hold its secrets close. Despite decades of research, dark matter's true nature continues to elude us. Scientists have proposed numerous theories, yet none have been definitively proven. But the quest to understand dark matter is far from over. Every new discovery brings us one step closer to unraveling this cosmic mystery. It's a journey that's pushing the boundaries of human ingenuity and driving innovation in technology and scientific exploration. The tools and methods we develop in this quest have far-reaching implications, and as we delve deeper into the darkness, we may uncover not only the secrets of dark matter, but also new insights into the fundamental laws of physics and the origins of the universe itself. This pursuit could redefine our place in the cosmos. The universe is full of surprises. Each discovery opens up new questions and possibilities. Dark matter is just one of them. It serves as a reminder of the vast unknowns that still await us. It's a reminder to keep looking up, to keep asking questions, and to never stop exploring the vast and mysterious cosmos we call home. Our journey through the stars is just beginning, and who knows what wonders we will find.